we learned about how you can count the number of primitive operations that's required for an algorithm to complete its execution. Especially we consider the worst case scenario. So why would this be useful? After counting the number of primitive operations, if you also know the exact time for each primitive operation to be executed in a particular physical platform. So just remember from one platform to another, for example, from one operating system to another, each primitive operation might take different amount of time to actually to be executed, even though the difference might be very small. But since we want to have precision, so we have to watch out for such details. Let's see exactly what I meant. Each primitive operation takes approximately the same constant amount of time to execute from a physical platform to another physical platform, but the exact time, the absolute value, might be different. And it really depends on the execution environments, depending on the operating system, for example, and also maybe the CPU load and other factors as well. And those factors should not be part of our concern about the algorithm design itself. So that's why it would be very nice if we can factor out those physical factors. We'll see. And the number of primitive operations required by an algorithm should be proportional to its actual running time. So what should be the extra factor that we're talking about? What's really the factor? Since we say it's proportional, so the factor is the exact running time for each primitive operation for that particular platform. Let's see. For example, this is a find max method that we just calculated, right? We talk about it got, in the worst case, 7n minus 2 primitive operation to be executed. And let's say for this particular t, right? So I talked about t earlier over here. Let's say for a particular platform t, let's say for Mac, t may be some number, and for Windows, t might be just another number. They might be different. But we can definitely factor out the value of t. And this will just be the number of primitive operations multiplied by the specific amount of time for each primitive operation to be executed in a particular platform. And now, let's say we got two algorithms to consider. One will actually take 7n minus 2 primitive operation to execute. The other one will take 10m plus 3 in the worst case. And let's say they are executed in the same platform. So now, would the exact value for that for the t really matter? You can see it's multiplied by t and also multiplied by t over here. So if you want to really compare these two algorithms, you can easily just drop this multiplicative constant over here. You can drop the t and drop the t over here. So you can just compare 7n minus 2 versus 10n plus 3. So what I'm doing here is I'm really moving from absolute running time into relative running time. So when we calculate, for example, 7n minus 2 multiplied by t, this is the absolute running time. But by dropping the t over here, given that every algorithm is going to be ideally or theoretically going to be executed in the same physical environments, the t over here will just be the same. So that's why we can simply drop them without losing any information. Right? It's a very important concept for you to grasp to see why we can, by dropping the t over here, we are essentially moving from absolute into relative running time. Right? It's really important. All right, so it will be sufficient just to compare the number of primitive operations. And to determine the time efficiency, all we got to do is to calculate the number of primitive operations. So after this slides, we no longer have to worry about what's really the exact value for t, depending on the physical platform. Right? I've got quite a bit of repetitions over here about the same point in this slide, but that's why it's so important for you to actually understand the absolute versus relative running time. Okay, let's move on. Let's now just revisit what we calculated before. Remember for the find max, we got 7n minus 2 primitive operations. And don't forget the n over there, according to our design for the method, n is simply the number of elements in the input array, right? Which can be a small number or it can be a large number. It's arbitrary. And let's say we try to be more explicit about the exponents of the n over here. You can see n here is to the power of 1. And also 2 over here, you can think about it's 2 times n to the power of 0. Remember, mathematically, n to the power of 0 is simply just 1. Right? It's actually easier for us to rewrite it in this way, so we can see the different powers for the variable n over here. Okay, so why would this be useful? So now we say n is the highest power over here, because you can see that what are the powers we have in this formula over here. We got power 1, and also we got power 0. Simply find the maximum. So that's why n to the power of 1 is the highest power. Of course, you might have multiple powers in the formula, in which case choose the maximum. That will be the highest power. And 7 and 2 are so-called the multiplicative constant, which I already mentioned in the earlier slides. So for n to the power of 1 and n to the power of 0. And if you got any extra factors over here, so these are the so-called multiplicative constants. And what will be the so they kind of symmetric. We got the highest power over here, and everything other than the highest power will be so-called the lower term. Okay, so lower term might contain several terms in the formula. In this case, we only got the remaining term, which is simply just 2 over here. Okay, or you can say minus 2. Maybe minus 2 will be more precise, but that's okay. So when you try to approximate a function which represent maybe the running time, let's take a look. So we only have to consider the highest power. So we will actually try to be more formal later, but for now, let's just get some intuition. And later on, we're going to define the exact mathematical definition for the asymptotic upper bound later. And the multiplicative constant and also lower term can simply be dropped. Let's do one exercise. You'll see exactly what I meant. And by the way, so the example that we're talking about, so by considering 7n minus 2, we're going to drop 7, we're going to drop 2, and also we're going to drop all the lower term. In that case, we only got n to the power of 1 remaining. So that's why approximately or asymptotically, you can think about 7n minus 2, by dropping all the irrelevant stuff, we can know that it's approximately n. Okay, let's do one exercise right away. So what about this particular formula over here? Okay, I'm going to write it on my iPad, but meanwhile, I would like you to think about how can we approximate it to be, okay, according to what I just said. Okay, so it's 7n plus 2n multiplied by log n. And in the case of, in this course, if we don't really say explicitly, whenever we talk about log, it's of base 2. Because computer is actually a binary, stores the information in the binary formats. So we actually talk about log. Whenever we talk about log, it's actually base 2. If it has to be a different base, I will tell you explicitly. Okay, log n and also plus 3n squared. All right, let me now switch to the notes over here. Right, that's the exercise we're doing. So how can this be approximated into? Approximately. Okay, well, what should that be? Well, let's now try to find out the highest power, right? You can see this is actually power, let's just be a little bit more verbose over here. You can think about this power of 1, and that's power of 1, and also power of 2, right? And if you, what will be the highest power? Well, basically, log n is actually strictly smaller than power of 1. So now if you multiply something that's strictly less than power of 1 by power of 1, it's going to be strictly smaller than power of 2, right? So the highest power should be this power of 2 over here, okay? So let's now make some annotation here. So the 2 over here is so-called the highest power. And let's talk about other terms which we also spoke about. So this is the highest power. What about multiplicative constant? So anything that's multiplied by n to some power will be the multiplicative constant. So 7 is, 2 is, and also 3 is. So these are the multiplicative constant. So these over here are the multiplicative constants. Multiplicative constants. Okay, and don't forget we can also drop the lower terms as we saw in the earlier part of the slides. So now how can we drop the lower term? Basically anything other than the highest power will be considered as a lower term. So all the remaining terms over here will be considered as lower terms. Okay, in that case, we can simply drop them, and we only drop them, and we only got sorry, let me say that again. Drop it, and then we only got this term left, but we can also drop the multiplicative constant. So that's why we're getting only n to the power of 2. So finally, we actually got n to the power of 2. So this is what we can approximate this formula into. So that'd be n to the power of 2. Right? I'm just trying to show you the steps, but usually it should be rather quick for you to actually judge what the approximation should be. Right? We will be a little bit more formal once we define the mathematical definition for the asymptotic upper bound. But for now, let's get some intuition. Okay, so that's highest power and then lower term, etc. Right? That's something we just illustrated. Let's move on. And we want to approximate the running time as a function on the input size, right? So given an algorithm, we can derive a function f, and the size of the input is going to be n, and the return value of the function is going to be the number of primitive operations that are performed on the input size n. Okay, so what does that mean? For example, you might have an algorithm that has the running time function that goes like this. If the input is of size n, in that case, he always requires 5 primitive operations for the algorithm to run and complete. If you got this kind of algorithm, it's very efficient. It's so-called constant time operation, constant time algorithm. What would be the more expensive one? So let's say locked base 2n, right? In that case, I will review the property of log when we need it. But for now, so this is slightly more expensive than constant time. If you plot the graph, you will see that the logarithmic plot is actually going to grow more steeply than the constant time function. You will see that. Okay? We'll actually got the graph summarizing the different functions. And the next one will be a so-called linear time function, right? So you can think about the different functions over here may well be just the running time for different algorithms, depending on which one you're talking about. So this is more expensive than this, whereas this is more expensive than this, and etc. Right? And the next one is so-called a quadratic running time. In that case, that will be to the power of 2. And then we can also get cubic running time. In that case, the power is actually 3. Right? Of course, there might be some multiplicative constant and also lower term that exist in the running time for the algorithm as well. But for now, I just want to show you the first time to make it simple, by making it simple. And finally, this is the most expensive algorithm you can get, which will be exponential. Okay, and that's something we might see later as well. So whenever you're designing your algorithm or you're trying to choose maybe something that's made available to you, you really want to maybe choose the cheapest one that's actually correct. So that'll be the judging criteria. That will be definitely the recurring thing throughout the course. We'll get there. All right, so this is simply trying to explain to you about the different kinds of cases you can consider. So we got either worst case, we got worst case over here, we got average case, and also we got best case. So let me help you a little bit how to interpret this graph over here. So think about the vertical axis over here is a running time, okay, for this particular algorithm, and the input, the discrete points over here on the horizontal axis is the different input sizes, right? You can see this is one particular input over here, and this is just another input, that's another input, that's another input. So you got the various running times. Think about this more like a statistical summary of the running times, similar to what we saw earlier. If you want to give the best case time for your algorithm, in that case, simply choose the minimum, right? Minimum running time, which is over here. Whereas if you want to know the worst case, and it should be here. So the implicit assumption. So what's the implicit assumption behind this particular graph? If I am able to tell you this is the best case and this is the worst case over here. So the implicit assumption is I have already covered all the possible shapes and also sizes for the inputs. Otherwise, I cannot really say this is really the best and there's no better one. And also this is the worst. There's no worse one, right? But that's kind of the implicit assumption. And what about average case time? Intuitively, average case time is just about taking the average for all the running time. But to be more precise, if you really want to calculate the average time, you have to calculate the expected running time, meaning that you got to use some technique of the probability. But we're not going to cover the advanced technique about calculating the average running time in this course. You might learn about it maybe more in your more advanced algorithm course in the 3rd or 4th year. But at least intuitively, you should know, in order for you to really calculate the average case running time, you have to actually apply the probability calculation to see what's the expected value for the running time. And what about worst case analysis or versus best case analysis? Which one should you actually perform? Well, that's something I already discussed with you. You definitely don't want to just quote the best case time for your algorithm, because in some way it's not very useful. You're only telling any potential user this is the best case specific to some particular input. But what about other inputs? In that case, you better tell the user the worst they can really expect. I think that's the way to really judge which algorithm is actually better. Okay. All right. Finally, let me just give you more a little bit of definition about asymptotic analysis before we see the mathematical definition. So asymptotic analysis, which I also mentioned quickly, briefly earlier, it's about describing behavior in the limits towards infinity. Especially we want to see how the algorithm's running time is going to vary as the input sizes grow very large towards the limits. Exactly what I just said. We want to see how the running time of the algorithm under analysis is going to change as the input sizes will change without any bound. Theoretically, of course. Of course, physically, if you only run experiments, there's got to be some limits on the input size. But if we do theoretical analysis, we are bounded by nothing. Right? For example, what would be the running time? What would be the asymptotic running time for this algorithm over here versus n squared? What I can tell you now is they belong to different families, strictly different families of asymptotic functions. That's something we'll see later. But at least you should see this is a linear function and this is actually a quadratic function. They're different. Okay. And the asymptotic analysis will actually allow us to compare the relative performance. Remember, we talk about relative running time by factoring out the t, the constant time for each primitive operation, which depends on the physical platform for execution, right? So now we talk about relative performance for the algorithm. And let's now see some example over here. But here's a principle. If your input is large enough, if you are given the function for your running time, for example, n and also n squared, you can always drop the multiplicative constant and also the lower order terms, the lower term, which we already illustrated to you how to do it. For example, here, after dropping all the lower term in this particular formula, you got only n left. N is the highest power, right? N to the power of 1. And similarly, this is the highest power is actually 2. So if you compare this one and this one here, because 2 is strictly larger than the power 1, so we would say this is a better algorithm in terms of the, I should say this is the more efficient algorithm in terms of the time. Okay, let's now see more example here. This is slightly more sophisticated formula. Take a look at this, and also take a look at this. Asymptotically speaking, after dropping all the multiplicative constant and after dropping all the lower term, so these two algorithms will turn out to be equally efficient because 2 is the highest power in both terms, right? So you can see for this particular formula over here, first of all, we drop the lower term. We drop this. And then we also drop the multiplicative constant, so we only got n squared left. Similarly, for this formula over here, we first drop the lower term, which will be this part here. And then we drop the multiplicative constant, which will be this part here. We also got n squared left, right? So asymptotically, they are equally efficient. And we'll do more example later. And similarly, how about this formula over here versus this formula over here? Well, asymptotically, as you can see the bullet points, after dropping all the multiplicative constant and lower term, we will get n cubed versus n squared. you can see the 3 over here is strictly larger than the 2 over here. So we would say this runtime function is going to grow much more quickly towards infinity. So that means the value is going to be way larger in order for this algorithm running time to catch up. So that's why we say this is much more expensive, meaning that it's actually much less efficient than this particular algorithm. So whenever you want to compare the efficiency for the algorithm, the less the running time, the better. Okay, the highest power for the running, the highest power for the running time function, the better, basically. Okay. All right. Let's now take a look at the kind of asymptotic bounds that we're going to learn in this course. We're going to first of all focus on the upper bound mainly for this course, and there will be it's called the big O notation, which we're going to define formally in the next slides. And you should also be aware that we also got two other asymptotic upper bound. One is called the lower bound. The other one is called the tight bound. So one is called omega, and the other one is called theta. Okay. For those of you who might be interested, you can definitely go to the reference textbook and then maybe study the definition. They are defined in a very similar way as the asymptotic upper bound, which is big O. Now for the course, we are mainly focusing on the upper bound. If there's any need, any time that we need the other two, I'll let you know explicitly. Okay. All right. Let's now formally define the asymptotic upper bound, the big O notation.